So, thank you very much. It's so wonderful to be here in this great ambiance, and thanks the organizer also from my side for this invitation. I would like to explain you how those types of cortical microcircuitry here can be described in terms of real-time dynamics to do such things as we heard, like deep learning, deep processing of stimuli and classification only in real time with those types of microcircuitries here. And I would like to thank already here those many collaborators without whom it would not have been possible for me to really dwell into the theory. And those helped me to also implement all those many ideas. I would like to start with this idea of the least action principle here, and start with telling you that this is a fundamental principle in physics first, where it explains almost everything, starting from the universe, where it explains the trajectories of those planets, stars, down to the level of atoms. And of course, the question is, what about then brains? Can you also describe the dynamics of voltages in the brain like that? And about behavior? What about those things, fundamental topics of our life? And in fact, there is an approach, you may know the general ideas of Carl Friston, who tries to map the ideas of the least action principle to those domains here. And we go along the same ideas, but start small with neurons, dendrites, synapses, and try to map those into the circuitry. But before going to our version, I would like to quickly present you the idea in physics. So there you have this action first that is defined as an energy difference here between kinetic and potential energy. And you define the trajectory in high-dimensional space that codes the position of all those stars here, for instance. You define the trajectory here to be on a path that does not change this least action here when you perturb a little bit the path. So these are so-called stationary trajectories of the least action. So think of a couple of planets that you're taking out and you're wiggling a little bit, and you don't change this quantity here. So the integral across this energy difference is to first order not changed. And from that you deduce a local law, the Newton's law of motion. That can be formalized locally, and that's done by those guys here 300 years ago, that locally you can get to conditions that must be satisfied to have this least action being really stationary across time. And this idea now transposes to these parts here, the brain and the behavior. And we are starting with behavior and try to characterize behavior in terms of learning, of course, with respect to an error. Behavior should be improved, and we have an error that directly translates into an error in motor cortex of neurons that produce that behavior. And we have to go further to tell an error to the neurons that project to those motor neurons. And we figure out it is this dendritic prediction error that is the key notion in our theory that links behavior to the neurons deep in the brain that lead to that behavior. So instead of this energy mix in physics, we are postulating that the least action is looking at the integral of the dendritic prediction error square of all the neurons involved in producing a behavior. I'm coming later, of course, to explain you how this is exactly formed. It's the somatic voltage first, and the dendritic prediction of the somatic voltage, and it is this difference in the dendritic prediction of the somatic firing that forms this dendritic prediction error, and that's the quantity within a single neuron, knowing how it relates to an error in behavior. And then we crank the same middle as physicists do for getting the Newton's law of motion, and we do get the Wilson-Cowan equations, but with one additional important ingredient, namely that that error here, also occurs here in the form of an error of the downstream neurons, of their dendritic prediction error that needs to be told to the upstream neurons, and this is entering here. The question is about how to bring that physically into the upstream neurons. But once it is there, we can formulate a local learning rule. Postsynaptic times presynaptic, but postsynaptic, it's not the action potential, it's really this quantity of the error. That's an error-correcting learning rule, and we can prove it is gradient descent with respect to a cost far away on the output neuron outside. If I'm a deep neuron, I'm doing gradient descent with this local error-correcting learning rule. And we get a kind of real-time error pseudo-backprop, and always thinking in terms of the trajectory of the whole brain. The whole brain can be described that is engaged in this computation as a trajectory of somatic voltage. Each point defines the somatic voltage of the 1,000 of neurons, pyramidal neurons, projection neurons involved in that task. And as a point, it moves in this universe of 1,000 dimensions. And we require that this trajectory is stationary with respect to this integral here, the same thing. And in order now to explain you this neural level definition on the level of the neuron of this dendritic prediction error, I have to start early and going back to the ideas that we developed at that time with Matthew Larcombe in this one early paper, where we tried to convince our third collaborator that even if you're in slides, we should introduce this concept of having top-down input to those slice pyramidal neurons that should predict what's entering in this basal tree, in the slice. And remember, these were new ideas at the time, and we really pushed hard to get these ideas formulated and not simply present data as our director at the time that both took us in his institute in Bern, tried to explain us how science is working, and we are very happy that at the time we really came up with those ideas together with Matthew. And we found that if this top-down input matches the somatic activation in time, we're getting a gain modulation of those neurons. And meanwhile, we are working on, and nowadays we are thinking of a learning rule that learns to do this matching, actually. And we are precisely here in an attentional mode, what we heard before. So we believe that top-down input learns to match the forward input here, and what we get is a kind of data-specific pseudo-inverse of these forward weights. That's another talk. Here I would like to explain you this idea of how now use this dendritic prediction error, so the error that you get with not being able to fully match what's entering here, by what the neuron here is driven. And so this idea of use this dendritic prediction error to adapt those synapses here. And here is this full circuitry. We have somatostatin neurons, we have other neurons that are inhibiting them, and we have this feedback. And right now in this configuration I'm showing you, it's just the same. We are operating in this attentional mode because VIP neurons are silencing those inhibitory neurons. And we have just this top-down input that predicts those activity here in the soma driven by the stimulus. But as soon as we are now inhibiting the VIP, they are themselves silencing SST neurons, and now we are in this non-attentional error-correcting code we believe is going on whenever we do things. We are seeing things, we are expecting things, they are going to be correct by visual inputs about the auditory system and vice versa. So this type of error-correcting learning learning is going on. And here is the idea. So we have top-down input entering here, trying to predict this activity here, sensory-driven. But feedback from these many neurons here tried to explain away what's coming from top. And if something here remains, this remainder is the error. You have a teacher, maybe more activity up here, that slightly depolarize this apical dendrites more than was expected. And so this is a positive prediction error. And this prediction error as a voltage propagates down into the soma, and we have first the learning of those inhibitory weight that now try to cancel what's coming from top. Is this Hepin plasticity and inhibition? They simply try to get a zero activity up there, and what is the residual there is this error that we interpret as an error coming from all these top neurons to which these neurons project to. So this is a back-propagated error. And this error now propagates forward to the somatic region where it adds to the contribution of those feed-forward sensory synapses. And together they fire to tell upstream, downstream neurons, and they also have this action potential that propagate back to the site of these synapses here. So they were producing their contribution, the U, to that overall spiking. They're getting now the full spiking that was produced by U plus the error, and so can, by subtraction, figure out what the error was up there that was told by all these upper layer neurons. And then they simply have to grab that error and do this error correcting learning rule, pre times post. Post is now this difference between the whole fiber rate minus its own contribution. And this is a couple of papers where we laid out that theory. And I'd like to come now to, before going to show you that this works, to show you that this idea of this circuitry is omnipresent in the brain, in cortex. Like here, I have described you in the version for cortical pyramidal cells that involve SST, but it may also involve PV neurons, for instance, to represent the generative error. That's one thing, but it also may appear in CA1, where perforant pathway here may be involved in the error representation to teach the Schaffer collateral. Or in CA3, we have the MOSI fiber input that may be involved in teaching the recurrent synapses for the recurrent memory there. And again, VIP neuron in all the cases may switch from this non-attentional to the attentional mode when you have a large error, and telling you this is now really important to be taken up into the representation, not this fine-tuning error-based learning. So coming back now to the results, and these are results with João Sacramento. We have heard him a few years ago, where we really implemented this idea in a network, also together with other colleagues like Sergio Bengio at the time, and he called those interneurons the ghost units, so various publications, and it works. So we could learn those MNIST sets here, as you can see, a nice performance, but I don't show you how quickly it learns. In fact, we have to wait 100 milliseconds for those microcircuitries to converge. And here, this new idea is entering, and would like now to become more formal about this least action principle, where we're solving this idea of having to wait until everything converges to a steady state. So here is the theory in more formulas that I was explaining you already. So we are simply summing up these dendritic prediction errors here of all the neurons involved in the network, and at a little bit of a cost. And then we do this kind of Euler-Lagrange equations. That's these Wilson-Cowan equations where you have this error here and do this learning. And there's a theorem that we do gradient-based learning for this cost here, and it is consistent with STDP. There is one important point, that we need to have this prospective coding, so this fiber rate here should look ahead. Otherwise, this error coming from top here always comes too late in this type of slowly integrating neurons. And if you look to the real neurons, also experiments done in Bern at that time with Michele Giuliano and Stefano Fusi, if you look at these pyramidal neurons, they in fact do have a prospective coding. If you inject noisy currents here into those neurons and record the spike train, you will see a phase advance, telling that they're looking into the future. And you're modeling this type of processing using this Hodgkin-Huxley idea. Whenever you have a fast activation time variable and a slowly inactivation, you get this type of looking ahead. So we can model this fiber rate of pyramidal neurons as not an instantaneous function of U, but a function of U looking ahead into the future. So think also in terms of fiber rate vector here. So this is telling you, go a little bit in the direction of the tangent of this big trajectory in high-dimensional space and take the point there where you're extrapolating, and that is the firing rate for the future, and process, please, that firing rate I'm predicting locally now. That's what those neurons are telling. And now we can really be in business with this physical theory of least action. That's the key thing. So we do apply this to our networks, and we can fit, for instance, intra-cortical EEG patterns that we get from the doctors, from humans, epilepsy patients, trying to fit those traces, and so on. Work in progress. But I would like to emphasize a bit more this idea of looking ahead in time. That's the key in the next application done with Mihai Petrovici. He is the key drive for that, where we also hope to have a physical implementation into hardware, because this theory, because it's really a physical theory, is now amenable to be mapped to hardware, whatever it is, also in the brain, as we believe. So again, the point is that whenever we have low-pass filtering, we are getting a delay. Starting from the input of one neuron I here, we're having a delay of the integration in time, and we look forward, and it is mathematically precisely the inverse operation what we do here of this low-pass filtering that we obtain by having these capacitors and integrating it and so on. So we're precisely aligned again here to get really the error that is shown at the same time as the stimulus, and we can process instantaneously with slow neurons. That's the idea, really moving in real time along this high-dimensional space. And we have this one nice paper here with a nice title, Arbitrary Fast Computation, here with arbitrarily slow neurons. This is much in contrast to what Wilson Cowan typically do. You always get a one delay, you know, of a tau. In a deep network, of course, getting horribly too late. And you could here, of course, also have the idea that you want to predict into the future by predicting a little bit ahead in time. And that's also work going on. But here, I would like to emphasize this one idea of having the instantaneous calculation with those real physical neurons that only think about the change in the voltage and from that extrapolate and look into the future. And that's enough to have real-time computation in this latent equilibrium. And here is one of the first results of the two I would like to show you, coming to the end. So here we apply those same microcircuitries to a very simple task, but everything here is learned, except the top-down connections that for that simulations we freeze, feedback alignment. But a very simple task here is first to just tell in 3 output neurons whether these lines are either horizontal, vertical, or diagonal. And now we learn at the whole time, with continuous time, we really present every millisecond a new of those patterns, rush, and have a long time constant of 10 milliseconds, simply going on forever, and everything is changing here. Synapses here are changing, those are changing, everything is dynamically changing, and is learning them to output the right thing. Here is the proof. And here I'm showing you the test error after learning. Now here, not as a function of time, but as a function of this presentation time I'm showing you. So here, 1 is the same duration of presentation as the time constant of the neuron is. That's what we use, and that's also the results of our old model we used at that time. We need to wait there 10 times longer, as we know. For still a little bit of conversions. Here it's instantaneous. We can really present for 1 millisecond these stimuli. And of course we ask what's happening if you go to more challenging tasks. And here it is. Here we take this LeNet 5 convolutional network, the same identical architecture, but simply replace the neurons with our Wilson-Cowan neurons, horribly slow, but add this predictive element plus tau u dot, which a neuron can calculate. And here too, we present those patterns here only very, very shortly, only for 1 millisecond, while again 10 milliseconds. And think now again in this trajectory of the planets in the universe I was showing you. This is the trajectory of the whole brain in principle, of this feed-forward path that we are simulating, that we're speaking about in these various talks here. That's literally the trace in continuous time. And this trace is moved around, minimizing while learning, while showing those patterns to become straight lines in some sense. Here to minimize this least action, to minimize the dendritic prediction error all over the network, and with that also minimize the output cost in a gradient fashion. And this, of course, was reverberating with me what Eero Simoncelli was telling that he is thinking of having these these geodesics that are formed with neural responses in response to a visual stimulus. That's what we have here in some sense. You know, we are really learning to move along such a minimal line where neither going to the right or to the left, you know, makes always the way longer, and that's exactly the definition of a geodesics. Here it makes this integral longer. So, of course, it's not only to you, Matthias, this task, or the question of Eero to check whether here we're using the curvature. In your case, it's likely here too we are using this curvature in that sense because it's set up in this way. That's it. This is my slide. The last one coming to, okay, this future work. Of course, I know your question is going to ask, what about spikes? What about memory? What about correlation? Work in progress, theory existing. And here is the summary. So we started out with this formulation of the least action principle, starting with this function, energy function, the summation of all this dendritic prediction error, cranking the middle, getting dynamics here, getting this microcircuit implementation of the dynamics, entering with this idea of Hodgkin-Huxley to have predictive coding, and we implement everything with real elements, with possibly real elements. We claim that actually the visual path has these options if it's set in a state, as we have in these experiments, to immediately process these Ornstein-Uhlenbeck type of experiments, to process these inputs immediately fast, to have an instantaneous calculation, to be tested, and we believe it's helpful for hardware implementation. And again, you know, those ideas, you know, can only grow if we constantly dispute them, explain them, correct those ideas. And thanks to Mihai, a group leader in Bern, to all those people, Joao, Dominique, many students who helped implementing those things that they always tell me, no, it can never work. And only after lots of work, you know, we got that thing running. And thanks, of course, also to people giving us always again money. Thank you, too.